So my name is Marnik van Kroost. Presentation, please. While we are waiting, so I'm going to talk about water. Water is life. Water is, of course, very important in the Sustainable Development Goals. And so I'm going to show you how how open science technology can be used to manage water resources. We'll first give a small contextualization of the problems and then say, well, how can we use open science technology for challenging the water data issue. Then I'm going to say something also about irrigation and water sanitation and how we can do that also with novel technology. Now, to set the scene, of course, water is a major issue. Basic natural resources, we need it for everything. It is important for energy production, food production. It is multidimensional, but unfortunately under a lot of pressures. And just to give you some key figures, nowadays still 2 billion people lack good sanitation. Nearly 800 million people do not have access to drinking water. Each day there is 1,400 children that are actually dying due to lack of water sanitation. And the map that you see here is actually showing where all the water shortage problems are occurring. And you see clearly that it is in the global south that we have a lot of problems, particularly in Africa. Also, to say something about food security, we need to eat each day. And of course, agriculture production is very important. Agriculture is a major sector that is consuming water at a global scale. 80% of the global water resources are consumed by agriculture, and 60% of actually the food security of the food production is done in areas where there is not enough of water, where you need to add water artificially by irrigation. 40% of the cereal production is actually also done in these conditions. So if we would like to address water issues, food security, then we need to also to look to irrigation, and that will be something that we are going to talk about. Now, if we would like to manage water resources at a global scale, we need, of course, to have data. And there is actually the problem that we have. We don't have enough data. Here, I'm just going to show you two maps showing the current status of two basic variables of the hydrological cycle, precipitation. Precipitation can be measured by pluviometers. Here you see the map showing the density of the available pluviometers in the WMO databases, and you show clearly that, of course, in the United States, Europe, we have a lot of data available. Unfortunately, if you go to Africa and Latin America, and it's particularly in sub-Saharan Africa, there we have a lot of shortage of good precipitation data. So that means that, well, if we do not know how much it rains, then it's very difficult also to manage the water there. The same for the global runoff water, so the water that actually flows in the river. We have also some availability of data that are available. It's the same image, actually. It shows also that a lot of information is available in Europe and the United States. But if you go to the global south, then of course you're lacking data of flow in the rivers, in the canals, in the lakes. And this is actually very problematic if you would like to manage the resources in a correct way. So this is a serious problem, data. We don't have it. So what can we do? Well, actually, we need to face this water data issue, and we can do it actually in three different ways. So I'm just going to show you some examples of how we can do it and on the projects that we are working on. The first thing is, of course, the Internet of Things, so the Internet of Water. So we have now smart technology that becomes available. Very often, if you're in southern countries, you have already a good internet, and of course, with the initiatives that are made by Elon Musk and his company, we'll have internet all over the world with a good coverage and a good power. And actually, well, if you have sensors available, which allows to communicate through this internet, then you can send this information about water parameters towards the server, and then you can, of course, through the internet, inform us about this kind of system. So just to give you an example, we are working on food production systems in Western Africa, rice production systems, which are cultivated in lowland systems, which are subjected to a lot of hydrological constraints because sometimes it's too much water and sometimes too less water. So we would like to know how much water is available. Well, within this kind of lowland valley systems, we install this type of piezometers in which there are sensors, smart sensors. They are actually communicating by GRPS through the internet to a servers in a University of Parakou in Benin. And there, well, actually we can consult, also here at distance, we can consult the information of the water level in this lowland system, and that is very precious in order to understand, for instance, how much water is available over there. Just another type of strategy that we can develop is, of course, and that's really the open science, is the remote sensing technology. In 2017, Google took a very strong initiative to create the Google Earth platform. And thanks to that, actually, all at sudden, billions of data became available, were disclosed, satellite data, which were not available previously. And thanks to that, we can actually also now use all this open science data in order to characterize, assess the water resources also in remote areas. Here again, also in these lowland systems in Africa, where we're actually using remote sensing data from different producers, as well from the NASA as from the ESA. Google platform actually allows us to console this. We set up algorithms in order to come up with interpretation of this data. With this type of information and technology, we can actually develop maps of some properties that are interested to us. So for instance, in this case, this is a time course of soil water, water that is available in the root zone of plants. And you know that, of course, it's in the root zone of the plants that water needs to be available to produce the plants. So what you see here is just a diachronic, a time series of maps of soil water within these lowland systems from 2019 until June 2022. It gives you the spatial distributions. You see that there is a rainy season and dry season, a rainy season and dry season. It gives you the spatial distribution of the soil water, and that can be used then to orient eventually irrigation in order to optimize the water application in this kind of fields. Another kind of examples, of course, we can use this, but where does it work? Is it appropriate? Of course, we have tested this type of technology. We installed in these type of fields also sensors allowing to measure in an independent way the soil water. And if you then compare the time series that are actually measured on these different probes, then we can see that it matches. Of course, it's not a perfect match, it needs to be interpreted, but at least we have already technology which allows us to monitor the time dynamics and the space dynamics of an extremely important soil variable that allows us to produce rice production in a correct way in these areas. Other type of issue, water quantity is of course very important. We need to be able to monitor that. Can we also look to water quality, given the fact that there is a very huge problem with water quality sanitation? Yes, we can. Of course, we can use also optical remote sensing, for instance, for monitoring turbidity or other parameters which are related to the emission spectrum of water. So here you see examples. This is not in Wallonia, it's La Meuse. It's also in the south of Belgium, but it's not the global south yet. So here you see, for instance, a time series of turbidity that has been measured in the Meuse on a station where also data were available. The scatter plot gives you some indication about the relation between what we can obtain from remote sensing as compared to a reference sensor. Of course, the match is not perfect. Measuring is also making some errors. There are always error contamination in the measurements that we are making. But at least we have already some trends, and the measurements give you some indication about how it works. Can we look to other parameters? Yeah, we can also look to other parameters, like for instance, chlorophyll concentration. Chlorophyll concentration is very often the basis of the primary food production in lakes, for instance. In lakes, if you have algae and chlorophyll present, then you will have fishes. And if you have fishes, well, then you know that this fish production can be exploited. And so here you see, for instance, the data that we obtained from interpretation of remote sensing data in the Lake Tanganyika reservoir. Lake Tanganyika reservoir, which is one of the biggest freshwater reservoirs in the world. It's actually feeding nearly 80 million people in Central Africa. Well, this is, of course, a very important resource, and we can actually monitor the chlorophyll concentration now with the open source data that are available. Here you see again also the time series of the chlorophyll data in this lake. You see typically, for instance, what happens when the season is actually changing, and you see, for instance, that all of a sudden algae blooms pop up. That's related to the hydrodynamics of the system. And this is very precious because it allows us also to look to the time series over long time. So what you see here is, for instance, the time series from 2000 onwards. You can actually see what are the dynamics of the chlorophyll, and you can do trend analysis to see to what extent this kind of chlorophyll concentrations increases or diminishes. And so also how this basic feed for the fishes increases or decreases in terms, for instance, of climate signals, which, of course, impact also very strongly the water resources in this area. Another type of approach that we can use in order to use our data acquisition systems is citizen science. Citizen science is actually the principle where we actually engage with the people to collect data on the water resources available, where we use technology like smartphones and internet in order to collect precious information. This can be done for water quality data, for water quantity data, but you need, of course, to have sensors that can be distributed to the people in a very cheap way. So here you see examples of a project that we have done in Tunisia, where we started working on precipitation. So we are collecting with different citizens, farmers, precipitation data. We have here the results, the black dots are actually the reference values, and all the colors are actually the measurements that are done by the farmers. And so it allows us to appreciate that the citizen science data are reliable. And so it gives you a very good information about what's going on in the system. It is also an inclusive participatory approach. So the people engage in contributing to the science, and that's of course very important if you would like to adapt and change the mentality of the people in this area. Other examples, use of smartphone technology for measuring discharges, and this is also working rather well. Or using, for instance, water quality strips. For instance, for nitrate or phosphorus concentration or chloride concentration, you can ask people to make measurements and make a picture of that, transmit it to a server, and have a look to that. Later on, we will have also Jean-Pierre Raskin, who will be in the panel, who will definitely talk also about his strips that he is developing for measuring Escherichia coli bacteria in water contamination. And you see that for some of these parameters, it works rather well. So we have definitely the possibility to improve our data acquisition and face the water data challenge with new technology. Something very fastly about irrigation, low technology. What can we do? Well, this is what so what we can do is, for instance, also develop technology that is very cheap, like for instance, irrigation, local irrigation, using this kind of technology that exists already by 4,000 years. So it's called pitcher irrigation. It is not very complex, but it is, however, it is technology in the sense that you need to design the good clay pitchers in order to have a good porosity so that it can be compatible with what is needed in the soil, and so that it can deliver the water that is needed. But what is interesting to see is that this type of technology is extremely efficient as compared to traditional irrigation technology. So we have, for instance, with this pitcher irrigation, we can increase the efficiency of the use of water with 100%. So it goes from 0.7 up to maximum 7 kilogram per cubic meters of dry matter. So that means that we can make an improvement, a serious improvement of our irrigation efficiency if you use these kinds of low-cost technology. The last thing that I will show is something low-cost technology for doing sanitation. We have, of course, a tremendous problem of water sanitation all over the world. We could imagine to install drinking wastewater disposal plants all over the world, but that costs a lot. If you see how much time it took already in Belgium for getting our water clean, so this is definitely not a solution that we can do in these countries. But what we can do is using nature-based solutions, like, for instance, these type of artificial wetlands, which actually can very easily also reduce the drinking water, the wastewater contamination. So it is also very simple technology. You need only to manipulate slowly the water fluxes in these plants, measure a little bit the temperature, and so with very low-level technology, you can actually develop something which is very nature-based, which works very well, like we can see in this type of tables. We can look to the results of the decontamination principles in this low-land technology. Just some key points to end my presentation. Is water a key in the sustainable development agenda? Yes, it is. Can we face the water data challenge? Yes, we can do it with Internet of Technology, open science, remote sensing platforms, and citizen science. Can we face irrigation challenge? Yes, we can do that with low-cost traditional irrigation techniques. And can we face the sanitation challenge? Yes, we can with low-cost nature-based solutions. So I'm very optimistic. Thank you for your attention.